projectile motion, what we attempt to control when we try and throw a piece of paper into a bin. When we release that piece of paper, or whatever it is we're throwing, we're obviously going to throw it at some angle and with some velocity, but of course once we release it, once it leaves our hand, we have no further control over that object. The only force acting on it is gravity. We end up getting that parabolic arc, as we just saw with the trebuchet and the fireball. Now, we could explore this using what we know about quadratic functions. At the end of the day, it's a parabola. So that's one way of doing it. But another way we can do it is by using what we know about parametrics, and where we break it up into vertical and horizontal, then bringing all the motion down again to simply straight line motion. By the way, maximum range will always occur at 45 degrees. 45 degrees. Okay, so our initial conditions on this object. We know that at time equals 0, we're going to release it, but we're releasing it at an angle. If I want to break everything down to horizontal and vertical, then I can work it out. Well, horizontal velocity and vertical velocity, horizontal over v would be cos theta, so the initial horizontal velocity will be v cos theta. The initial vertical velocity, v sine theta. Okay. Initial displacement, it's whatever we choose to set the coordinates at. Most of the time we'll just set it as the origin. It makes life easier for solving problems. So x equals 0, y equals 0. Alright, starting point. All we know is what's happening with this particle is gravity's acting on it. So horizontally the acceleration is 0. Nothing is happening horizontally as far as acceleration goes. Vertically, we have this one acceleration, gravity, and it's in the negative direction, so it's minus g. So to work out velocities, we integrate. So I'll get a constant for horizontal. For velocity that is vertical, we get minus gt plus another constant. Okay, when t equals 0, we worked out our initial conditions, so we can sub that in and work out our constant. So horizontally, we've got a constant velocity of v cos theta, which was its initial one, whereas vertically, minus gt plus v sine theta. For displacement, we can integrate, and the same vertically. Again, I've chosen them nice and neat, so 0, constants turn out to be 0 that way. And we end up with equations for displacement. So with those equations, I should be able to solve any problem. I've got equations for both vertical and horizontal direction, for displacement, velocity, well, acceleration, don't really use those that much. But we have got it in parametric form. The parameter, of course, is time, t. So basically, they're the parametric coordinates of a parabola. Now, we're used to seeing the basic one where the vertex was at the origin, but it was 2at at squared. But if you think about it, x was just simply a multiple of t. Well, yeah, x is a multiple of t. In this case, it's v cos theta. And y was at squared. So a multiple of t squared. Yeah, well, that's what we've got. Okay, there's some shift happening, but we've got a multiple of t squared there. Okay. Now, t, I could rearrange x on v cos theta. I could sub it in, eliminate the parameter, and we come up with the Cartesian equation eventually. Tidying up, we've got sec squared plus x tan. Nicer to make it all tan so it looks the same. We end up with a quadratic equation. So gx squared on 2v squared and so on. So it is possible to create the Cartesian equation. And then we have a choice how we want to work with this. Do we want to work with it using parametrics, or do we want to use our Cartesian equation? Common sort of questions they ask, standard sort of things that they know. Oh, when will the particle hit the ground? I mean, y would have to equal 0. So what's the range of the particle? Well, range, how far has it gone? Once I've worked out when it hits the ground, I can sub into x and find where it hits the ground. Of course, if I was using the quadratic, the roots of the quadratic, or the x-intercepts, would end up being those points. Greatest height of the particle. Well, what's going to happen to the greatest height? Because before it can start coming down, it's got to stop. So once it's stopped, it's not going to go up any further. So let's find when the vertical velocity is equal to 0. That'll give us the time. We can substitute that into vertical displacement. That'll tell us how high it goes. If I'm dealing with the quadratic, we're talking about the vertex of the parabola. So we can find the vertex. What angle does the particle make with the ground? Now, if you've released from the ground, then the answer is really easy because it's a symmetric shape. So if I've thrown at an angle of 30 degrees, then it will hit at an angle of 30 degrees because of symmetry. We'll find when it hits the ground, substitute into, and we use the velocities to work out the angle. So it's the velocities we resolve. So we find y dot. X dot is of course constant. Draw ourselves up a triangle and we can work out the angle that it hits the ground with. If you were using the Cartesian, then basically slope of the tangent when it hits the ground. That would be what we're looking for. So you'd find the slope of the tangent, and slope of course is tan theta. And then you can get the angle. Alright, so summary. Anything undergoing projectile motion, we know simply this, and that is it. That's all we know. Okay. Then through calculus, we can derive the other things. We also know the initial conditions, of course, that we release it with. So those things we can just quote, that's fine. Everything else we derive. Lately in the HSC, they've been giving you a lot of the equations to save time. And they'll say, the equation's given by this, and they'll put a little note, do not derive this, or something like that. But if they haven't given it to you, then obviously you'll need to derive it. Okay, we're going to throw a ball, 25 metres per second, angle of whatever the inverse 10 3/4 is to the ground. So let's answer some of those common questions. The greatest height obtained. So, initial conditions. Draw myself up a triangle. X dot is v cos theta. So in this case, it'll be 20 metres per second. Y dot v sine theta, 15 metres per second. I'm conveniently using 10 for gravity rather than 9.8 just to make the maths a little bit nicer. I never said I was on Earth. I could be on another planet. You never know. Okay, and well, it's the same process. We integrate, work out our constants. There's my velocity equations. Integrate again. And we get our displacement equations. So we're trying to find when velocity or vertical velocity is equal to 0. So we solve that. We now know 1.5 seconds. So if we want to find the greatest height, substitute it into our y displacement, and we get 45 on 4. So once we've got our equations, it's a little bit of logic and a little bit of substitution, and we'll get what we want. The range. Okay. Well, again, I can use symmetry here. I can work out the time of the flight straight away. If I know it took 1.5 seconds to go up, by symmetry, 1.5 to come back down as well. So the total time of flight, 3 seconds. So sub that into x, and we get 60. So there's our range. So after half a second, what is the ball doing? Will it be going up or going down, by the way?
Up.
Why?
Because it's less, it hasn't reached the maximum.
Yeah, because we said 1.5 was when it reached the top, so we know it's going up. So after half a second, constant velocity of 20 horizontally, vertically is 10. Remember, we use the velocities to work out the angles. And then I can just draw myself a little picture there. It is going up. And I know the angle is 26 degrees 34 using a bit of trick, and the velocity using Pythagoras 10 root 5. There we go. Cartesian equation. Alright, so eliminate the parameter. So t is x on 20, subbing in, and there's my quadratic. So now that I've got that, let's do the same problem but using the Cartesian, just to show that, yeah, we will get the same answers. So greatest height, now I'm talking about the y value of the vertex. which you may recall is minus the discriminant on 4a. So the discriminant for this one's 9/16 minus the discriminant on 4a. Yep, we get our 45 on 4. What was the next one? The range. Okay, I've factorised this so I could find the roots quite easily. Obviously one's going to be 0 because that was where I was leasing it from. So the other one must be the solution to 3 minus x on 20, which is of course 60. So there's our other one. We then said velocity and direction of the ball. Well, I've got to work out where it is if I'm going to use the calculus. Because remember, I've eliminated t, and all I knew was after half a second. So I'll find the x value there, and it's equal to 10 when I sub it in. So the derivative is minus x on 40 plus 3/4. Sub in x equals 10. The derivative turns out to be a half. 10 of a half, and there's our 26 degrees 34 that we came up with before. The velocity, and then we can just sub it in, and there we go, 10 root 5. Okay, so 3g and 3h